mathematical proof. Uh, as mentioned in the book, mathematical proof is we have a true statement, true, let's say, mathematical statement, and we will give a logical and a structured argument. And we'll come to the conclusion that this is always true. Then it is become theorem. Now you have a true mathematical statement. You want to give a logical and a structural argument, and we'll come to a conclusion. This is always true, and then this true mathematical argument become theorem. Now, when you give this logical and argument, still you are sometimes using the axioms, previously used theorems, prepositions, lemma, and corollaries. Previous stuff, and then you become a theorem. And when you give this argument and show that is always true, this is become a theorem. That's how it's more. This process is usually called deduction. There are some statement in maths. There are two mathematical statements, but we can't prove this one, or not to be proven. Nobody can yet to be proven. So these are called conjectures. A statement which is to be believed, a statement which is believed to be true, but do not yet have proven. We know it is true, but no mathematician couldn't prove yet. So one good example is Goldbach's conjecture. Goldbach's conjecture. It's very simple, but no one couldn't prove yet. That is, every even integer, you can check this one. Every even integer greater than 2 can be expressed as a sum of two primes. This is very simple now. Goldbach's conjecture, every even integer greater than 2. Okay, I'll pick up any integer Even integer greater than 2, I will pick up 4, can be expressed as a sum of two primes. 4 you can write 2 plus 2. Those are 2 primes. Any other integer. 6 you can write 2 plus 3. Both are primes. 20 you can write 3 plus 17. 15 you can write the 2 plus 13. So not 15 is not a even integer. It can be 16. 16 you can write 3 plus 13. Those two are prime, those are prime. Every even integer greater than 2 can be expressed as a sum of two prime numbers. This is true. But still nobody could prove this one. So this is a famous conjecture, Goldbach conjecture. Some other things you may learn in the future. Sufficient condition. If and necessary condition. Only if. And when they come together, necessary and sufficient condition. This is if and only if. So when you have a time, just read these things. Especially student who is planning to do maths in universities, they should know these things accurately. Sufficient condition, necessary condition, and yes, necessary and sufficient conditions. Usually we use symbols, this direction and this direction, and if and only if it's going to be, it's both direction. For example, if x equal 2, then x square equal 4. Now you can write x equal 2, then x square equal 4. You can use this symbol, but you can't use the other way around. X square equal 4, then x not equal to, because x equal 2 is wrong, because x has to be plus or minus 2. So in this case, um, this side is not applicable. So in that case, it's not if and only if. You can't write x equal to, you can't write x square equal 4, because if you can write, it should be work both ways. If x equal to x square equal 4 and x square equal 4, then x equal 4. Now x equal to x square, if you write this one, this is wrong. This is imply when x equal to x square equal 4 and this x square equal 4, then x has to be so 2, which is not right. Hence you can't use this symbol, because this is not right. It has to be plus or minus. So this is just an idea about that uh, if and only if. And just it's a general, try to give a general idea. Assume that you have a cat at home. So this cat has a tail. Okay, this way is right. Now you have a tail. You can see, assume you have killed it. Then it is only the cat. No, it can be a dog, or it can be a horse, or any other animal. So this is, then I can apply this one, uh, and this is the tail, and I can apply this symbol. It's not if and only if, because it doesn't work the other way around. Yes, cat has tails, but the animals who got all tails are not cat. So this is like this. Then proof techniques. There are some proof techniques. We are not going to use all. We are going to use only one. One technique is proof by contradiction. This one we use in the second year book. We we take this statement is P. Now this is one we want to prove. Then we assume P is false. We assume. Then we derive a contradiction from assumption, because we made a wrong assumption, hence the statement has to be true. We made the wrong assumption, hence the P is not false and his statement is true. That's how it works. You can't understand. I know that we will discuss when necessary. Another one is proof by contrapositive. And when you look at proof by contrapositive, what is contrapositive? Just to give an idea. So contrapositive means you can write a statement in other three forms. One is statement, then converse, then inverse, and the other one is contrapositive. Assume that statement is if A then B. The converse is if B then A, and inverse is if not A then not B, and contrapositive is if not B, converse, negation of, so negation of the converse. If not B, then not A. Right? Assume statement. If it's sunshine, then I am happy. See the statement. Now the converse of this one. If it is, if I am not happy, then sunshine. Then, sorry, the converse is this. If I am happy, then it is sunshine. Don't think about right or wrong. That's how it is. If it is sunshine, this is the statement. Sunshine, then I am happy. Converse is if I am happy, then it's sunshine. Then the inverse is the negation of this one. If it is not sunshine, then I am not happy. Inverse is if it's not sunshine, then contrapositive. Negation of the converse. If I am not happy, then it is not sunshine. So when in a statement we can write in these four forms and we pick up only this one, contrapositive, proved by contrapositive. Another one is proved by counterexamples. Another one is proved by induction. You can see general guidelines when you write a statement in a mathematical proof. You must state any information assumptions you are using. Show every steps and proof clearly. Make sure that every steps follow logically from the previous step. Make sure you have covered all the possible cases. Write a statement or proof at the end of your working. So that's how you want to uh, do. And to prove an identities. Identities mean always identical. Um, the one is given in this one, a plus b, a minus b. And we use this symbol, a square minus b square. This is fixed. If we want to prove identity, uh, usually we start with left to right or right to left. So we take, okay, I'm going to show this identity, proof of this identity. So I have already used this kind of actually. A minus b equal a square minus b square. Now I start with left side. Left hand side is a plus b, a minus b. Then I am writing a times a minus b plus b times a minus b. Then this is a square minus ab plus b a minus b square. Then a square minus ab, I can write this one as ab minus b square. Then what will happen? This is cancel out. A square minus b square equal to right hand side. So I prove the identity. So that's how you want to use uh, prove identities. If you plan to do maths in university, this is a good book. Peter J. Cameron is a really good professor. Introduction to Algebra, but you can't understand this one when you look at this is not A levels, but if you plan to do maths, this is a very good book. You have to read and understand. And some other books. This is also Franco mathematical writing. It will show how to write mathematically and proofs and also it will cover the grammar and writing tips, dictionary, An essential dictionary, mathematical syntax, describing functions, writing well, right? Proof, how do you give a proof? How you give a proof, and induction, and this kind of lot of topics. In here you can see in this introduction to algebra book, you can see that introduction area, arithmetic, numbers, and then rings, group, vector space, modulus, the number systems, and yes, and further topics. This is a really good book. This is not A level algebra, but it is university. So if you plan to do university, maths in university, so those are the stuff. This is other book of proof, uh, and this is also a good book. There are a lot of proof there. You can look and you can practice, but not for A levels, but still you can go through. In this book, example 9, that's a good one. If x minus v is a factor of fx, then show, uh, then yes, we have to show, okay, show fp equals 0. This is example 9. If xp is a factor of fx, then fp equals, you want to show fp equals 0. If f is a factor, then you can write fx equal x minus p times gx. Fx equal 4x cubed plus 4x square minus 11x minus 6. This is number 14 sum, and x minus 4 is a factor of this one. Sorry, x plus 2 is a factor of this one. Then fx you can write x plus 2 times, we divide this one, 4x square minus 4x minus 3. It means fx x plus 2 times, what is this one, another function. So this is the thing. If x minus is a factor of xx, then if v equals 0, then we want to show that, then if f minus is a factor of x, then I can write xp times another function, x plus 2 times another x function of x. Now we want to put fp equals 0. Now I'll put fp. Then what is happening? P minus p gp. P minus p become what? 0 times equals 0, done. No? Now I want to put x minus 2. What will happen this one? Minus 2 plus 2, g minus 2. 0 times g minus 2, f minus 2. This is become 0. We'll discuss more in exercise 7D. And if you are not sure if you could understand what I said so far, because just I glance, and you don't need to worry, you will be eventually you will get it, this one, when I discuss these examples.